Hi, welcome back to a new episode from the series Data Privacy with Machine Learning. In this episode, we are going to start up with setting up some main assumptions based on the ideas we have established in the previous session. And then we'll be looking at a lab illustration on breaching privacy in the previous episode, where a linkage attack, given the data set or the case study of the Netflix price. So we will see a real example simulating that and using the two data set we have already created in the previous episode. Following that, we will discuss in depth the advanced concept and techniques of anonymization, which is one of the leading techniques when it comes to dealing with the privacy. And finally, we'll be looking at a lab illustration on the discussed techniques of anonymization. Let's go ahead and start with the first outline of this session, and that is to set up our main assumption. Essentially, there are two ways to access a data set, as I have established in my previous session. The first is to consider query scenario, and the second to consider shared copy of the data set. Now, as I have said in many materials discussing the topic of privacy and data, they fail to clearly and explicitly actually mention the two scenarios. And I think the contribution I have made, even in the academic paper that I published about the subject, is to differentiate these two scenarios, because the techniques would look like quite a bit overcomplicated if we don't really know which scenario we are belong to. To this end, I wanted to start up with a reminder of these two assumptions or these two scenarios. All right, so let's first of all start setting up the lab to see a simulation of the linkage attack that we have seen as a case study in the Netflix dataset price story. Basically, what we want to do actually, we want to see something before applying anonymization. I mean, a proper kind of anonymization. Not only about removing the name, because we know now removing the name does not really protect the data set. To this end, we are going to imagine a scenario of both assumption, sharing, and query. Both of them will take place in this particular lab. So what we will assume that the Techqniques company made their data set available for query. For the second data set, the telecommunication data set, we assume an accessor have a shared copy of that data set. The scenario is going to be this accessor can query the health data set, which is belong to Techqniques company. At the same time, he or she has the data set from this telecommunication company in their premises. Let's see if this scenario happen, what kind of privacy violation we could experience. Let's go ahead and see the lab illustration. If you are following up from the first episode, I think this Jupyter node should be familiar to you. So I have created here a class called a privacy class with number of functions in it, as you could see here. Now they are all linked and related to each other to illustrate a few examples. Essentially, we will start first of all with the case we imagine accessor has created this class. Can query the data set that is somewhere on the server, and whatever result returned from that query, I could match it to the dataset that I have in my premises. This is the illustration I'm showing you here. So I will imagine the query looks like this. So the Techqniques company says you can query from my site or on my server a specific kind of queries. For example, can you return for me a gender of 0 who lives within the zip code area of 35 and has the age of 50. We could obtain then number of cases matching this query in particular. But at the same time, what we want to do, we want to take the same query and match it to the data set or the telecommunication data set we have it in the premises. And from both of them, we try to make matching to the return case and make a probable how likely is a person that we know. Given the fact, by the way, that we assume the data set of the telecommunication company is generated for that particular region. So to make the things or the scenario looks more real, we don't want to say like I obtained a data set from another country and I go and try to match it to another data set or query from somewhere else. So we are consistent with the scenario or simulation might take place like this. So the first data set or the first function I want to share with you after creating, of course, instance from this class called private class is to call on this particular function. It's called linkage query breach. Now, this particular function, it does exactly what I said. I assume that I can query the anonymized Techqniques dataset server, and then at the same time, I am matching on the query with the dataset that I have on my premises. So you could actually look at the code on your own. It doesn't have too much complicated lines, and I make some actually a clear documentation on it, so you won't get lost anyway. So let's try to run this function and see what is the return. This function, by the way, it takes 3 arguments. It takes the first data set, and this one should be the query return from the Techqniques company. So, but I put it like as if it is the data set, but usually it seems to be like the query. And here is the real data set that I have, the telecommunication one, and the query, of course, itself. These are the 3 arguments this function takes. So if we run this data set, let's see what happened. I just wanted to show you the first 10 entries from the data set that I have in my premises, the telecommunication one, which has the name, the customer number, the age, the gender, etc., as we have seen in the previous episode. And these are the 10 first entries of the dataset that we assume not within our hand. It looks like this. So it seems to be anonymized with no names. Anyway, but the point that what we're interested in is the query return result. You could see here this result returned from my data set. It shows there are actually 2 hits exactly matching that kind of query. At the same time, the query returned from the dataset of Techqniques, it seems to return 2 again cases. Now, there are no names, of course, but the age is matched, the gender is matched, and also the zip code is matched. And you could see here the sensitive information of the disease with diabetes or without diabetes. So we have here both cases returned based on this query with the diabetes. So what conclusion I can make? Well, it's highly likely that these 2 people are actually these 2 people. Now I know this person is highly likely to have the disease of diabetes according to the matching kind of result returned from the query and also from the dataset. It seems to be perfect example matching 100%, but maybe in much more real setup wouldn't look like because we already tailored the dataset to look like this. But this is what happened. Even if imagine 3 results returned from the query, not only 2, it means the probability will be reduced, but still within the context that I wanted to illustrate the meaning of linkage attack, most likely in the cases where you have this kind of setup. So I wanted to show you this to tell you the query on the Techqniques dataset, the server did not preserve any privacy attribute into their answering for those kind of queries. To this end, what we want to do, we want to enhance such feature by integrating the privacy to some of the features that are actually queried at the first place. Let's go ahead now to our slides and continue the discussion. So before we speak about the details of this anonymization technique, I wanted to share with you the most common available techniques has been developed over the years. The first technique, it seems to be known for quite some time now, is the anonymization. It started just by removing the name, but later on with the linkage attack problems, started to improve and integrate different aspects of this kind of anonymization, which we're going to discuss in details in a while. The second technique called restricted query, which usually says before I answer a query, there are some restriction or rules. Example, you cannot query a dataset by saying, is Mr. X in this dataset? That's a direct query and shall be the server not answering such questions. However, it turns out that there is a way to go around this by using something called a predefined question. So you don't actually ask directly about Mr. X, but you have some information about Mr. X, and you start to query the data set with 3 or 4 questions, but you know the link of these answers, it will reveal some privacy at the end. And the third technique, known as the homomorphic encryptions, as the name implies, it means, especially in the case of machine learning, that usually we send the whole training data set. I mean, the feature itself, imagine it as a vector. I send it as it is. But with the homomorphic encryption says, well, we don't send the value, but we send an encrypted value. And then the server can do some computation on this encrypted value and return back an encrypted answer. And then I can get the result that I want. But you could see here as I am talking, the space and the time complexity seems to be overwhelming because the transformation to an encrypted vector of value could be really costly. And that's why this kind of technique, it's not really seems to be efficient in many kind of different setup. And the next one is called the federated learning. Basically, it says, let's train on the local machine. Another word to say, instead of sending the data to the math of the machine learning, let's send the AI algorithm to the client side. And finally, I can aggregate all these updates together from different clients. Well, it seems to be promising. We're going to discuss also federated learning in the future sections. And also, we will demonstrate a case on it. There are some downsides in it. For example, if the connectivity between the client and the server is not really strong enough, maybe you will face some problem. In addition to that, in recent publication, it's proven that there is a problem of memorization issue. It means the model still can memorize specific details about clients that might be revealed once it returned back. The last kind of technique, which is the most prominent one with a mathematical foundation, and we will have really in-depth discussion about it, it's called the differential privacy framework. So the basic idea is to add noise to the feature. Now the problem, it turns out also with such a technique, it's a prediction quality, especially when it works with machine learning algorithms, because you are adding noise and you are worried also these noise can affect the accuracy and the efficiency of a machine learning model to learn. But anyway, these are the most available and current promising kind of techniques. We're going to discuss all of them in details and with some certain examples as we go along the way. Let's start first of all with this anonymization technique and see what happened over the years. Now, the first thing to introduce you the idea of anonymization, to discuss the concept of K-anonymity. And what does that mean? Let's look at this data set, which I have a snapshot from a training program. Again, I will leave it for a reference if you like to get back to that. You have this data set that contain name, age, gender, zip code, and some kind of disease. I mean, the standard one we've been talking about for quite some time. The first idea of anonymization was to remove the name, of course, and we know now that is not going to really work, especially with kind of linkage attack we illustrated. So the K-anonymity, the first thing it does something called generalization. And basically generalization means instead of spell out the particular value, why don't we create a range or a bin contain a certain ratio of numbers, and that particular value will fall within that bin. Take, for example, instead of writing 28 years old as an age, I could create a bin of 9 years between 21 to 30. And we say, well, 28 fallen within that category or within that group. Same for the next value of 17, 34, and 41. But you could see here, for example, if I have taken such a generalization aspect, I'm still unable to protect the data completely because I'm still able to identify there's only one guy fallen in that category of 21 to 30, and he's 28 years old. So I am still able to say he's a female, she's a female, and this is the zip code, and this is the disease. To this end, why don't we extend that group or that range a bit wider, make the bin 20 years, for example, or 19 years. And it's exactly what you could see here. When we've done that with the age from 10 to 29, we have 19 years gap. In this case, the 28 years old and the 17 years old, they will fall in that group. So I have achieved here with the age feature K-anonymity of 2. And it's obvious why 2, because there are 2 groups right now. However, if I look just next door to the next feature of the gender. In the first group, this group from 10 to 29, if I would have information, I could identify which one is which one by just looking at the gender, where in this group we have a distinguished one with a female and male. To this end, we could say because of problem with the gender, now the K drop 1 to be 1. All are identified. Same for the zip code, of course. That's why the next improvement on such anonymization technique is called suppression. And basically, we have seen in the case study, or the third case study in the previous discussion, where the suppression has taken place with letter D, for example. So I'm not revealing any information. Why I have decided that? Because it seems if I reveal it, it will actually reveal some specific information about individuals. So in this case, instead of reporting female and male and in the gender for the first group, 10 to 29, I just want to suppress all this information as well as the zip code. However, here, the drawback, if I keep doing that, maybe I will lose my ability even to learn anything at the end. So what is the purpose then? We need to trade off. I mean, we have to find out that sweet spot where things has to give me some information, but at the same time, try to preserve as much as you can privacy concern for individuals. So what I have achieved in this third picture is a K anonymity of 2. And I just suppressed the gender and the zip code. But at the end, I could also integrate both of them. Like this case, we have the age and the gender. And maybe I just mix both of them with some generalization and suppression, and I end up with such data set, I would say with K anonymity of 2. But as it turns out, and I think you should be figuring that out on your own, the K anonymity appears to be effective when only the data set entries are diverse. In other words to say, if it happens that I make this group age from 10 to 29, but still I only have one person falling in that group or only 2. So the probability of identifying their disease or whatever sensitive information I'm able to learn about, it becomes quite a bit obvious. That's why K anonymity on its own completely does not really guarantee 100% privacy preservation at the end. That's why in the second improvement on such a framework come with the concept of L diversity. And basically the L diversity, as the name implies, it shows you how much diversity happens in the data set. Let's look at this continuous example on the same data set that we actually have done some generalization and suppression on it. And we achieved K is equal to 3 anonymity. So we have this age 3 groups of 20s, then 40 to 50, and then 30s. Zip code also was kind of generalized and also suppressed. But then we look at the diseases. Now, when you look at this case, it is obvious to observe a problem. If you have a pre-knowledge of a customer that participated in this study, and then you know their age, and then you know their maybe zip code, it is not hard for you actually to spot directly from this K equal 3 anonymity, which person and what kind of disease they have. Because here in the first group of 20s, all the people in that group, they have heart disease. So it's obviously if I know the person within that age and within that zip code, I could easily say, well, highly likely this person has a heart disease. That's why L diversity, it gives me the ability to quantify that risk. So in the first group of 20s, there is L is equal to 1 because all of them are identical. But in the second group, for example, I get like L is equal to 3. And then in the third, I have L is equal to 2. So you could see the L diversity, it helps you to understand how much diverse the information. And based on that, I could maybe suppress some of the diseases. Maybe I could like shuffle the data set. As they end up with this data set, the final quantifying of this data set looks like from metric perspective that we achieved K anonymity of 3 and L diversity of 3. But the question is, again, is the person that we were talking about, is he safe now? Well, not really, because if we look at the salary side, we could see quite clear that 3, 4, and 5 is the lowest kind of salary in the space of all the salaries. So these are the smallest kind of salary or income. And if we look at the diseases and categorize all the different diseases that happens to be in this data set, I could say this person had some problem with their stomachs. So in general, we still have risk of revealing information. That's why we move to idea of T-closeness. Now, T-closeness is the third improvement on anonymization technique in general. What does the idea of T-closeness basically do is to measure a distance. Now, what distance we are trying to measure? Imagine we have achieved this k is equal to 3. So we have a group of 20s and 40s and 30s. And also the diversity has been accomplished as well. If we take only from the perspective of a feature as the age, so we have these three different groups. If I take each one of these a group and I measure how far is this a group from the general norm of the entire data set. So if you have like all the space of the ages, and I have this particular group, the 20s, I want to measure how far it is from the actual entire norm of the data set. That's the concept of distance, hence what we mean. If we capture that distance, it will logically be the shortest the distance is the best that privacy will be preserved. But if you are far, it means you are distinguishable. So that's why this kind of K group, if it happens to have a large distance from the general norm of that feature, it means you are at the risk to say this group will reveal information. And this is a very, very good idea in my opinion. Now, question is how to calculate that kind of distance. Well, there are so many different techniques. You can check the references that I have left for you in the academic paper. In particular, in the literature, the Earth mover's distance seems to be the most prominent one of use. Basically, it does exactly what I have said just now. It just measures that kind of distance between a K group and the entire norm. So if you look at the data set, two features I picked up to measure this kind of distance happen to be a numerical, like the celery, and the other one happens to be categorical, like the disease. Let's look at the case of this numerical celery calculation. Now, what happened is let's organize all the celeries, possible outcome of celery in ascending order. So we have like from 3 to 11. These are the possible outcome of celery happens in this data set. Now, let's take the first group or the first K group. It happens their celery 3, 4, and 5. And let's take another group that happens their celery to be 6, 8, and 11. And we want to measure this P1 from the K, and again we measure the P2 from the K. And we use the formula that you see on the screen just by taking each distance and masking by 1 over n. Now, as a result, if you measure the distance from P1 to Q, you get a distance of 0.375. And we have another value of 0.167 for the second group. What does that tell me? I can come to the conclusion that K1 group, the 20s, seems to be more risky to reveal information about individual than the B2 group. Now, when it comes to a categorical case, such as the disease, what we can do, we can create kind of a tree, and this tree has some hierarchy or levels, so to speak. So in the head, we have the mother of these diseases. Then I can create 2 different groups, and each one of them has their own 2 different branches. And finally are the last node. And basically what I want to do, I want to measure the distance between each one of these last nodes in the tree. For example, if you take this colon cancer and its distance from the next disease, the colitis, for example. So both of them are sharing the same branch or the same node, the mother node. In this case, their distance will be 1 divided by the total number of branches or levels in this tree. In this case, we have 3 different levels. So this is the first level, and then we have this, the second level, and then we have this, the third. So it is 1 over 3. But if you go to the second one, between colon and stomach cancer, you could see now both of them are shared with the second level of the tree. So the distance will be 2 over 3. And if you take this colon and its distance from any disease on the left-hand side of this tree, for example, the flu, you will find a distance of 3 over 3. That is 1. This is the maximum distance you can get. That's exactly the procedure is going to go on by doing the same exact thing, by creating P1 and P2. This is the first group, K1 and K2, and then measure the distances, and you will find from 0.1 to Q, it's 0.5, the other one, 0.278, which is less than 0.5. So I can come to the conclusion again that seems K1 to be risky to reveal more information. If I make some arrangement and shuffle based on this information I have just learned, I could come with the final kind of data set would look like exactly as you see in the screen. In this case, what I could say, I have accomplished a 3 anonymity, 3 diversity, 0.65 for closed celery, and 0.78 for closed disease. This is the metrics that are actually presented in the academic setup or a discussion in the industry. When you have a data set, you can actually brag on these measurements that if you have accomplished them in the first place by guaranteeing your customer to be safe. Let's go ahead and actually apply some of these techniques we've just learned. So I'm here back to the same result that you got just now. Let's say that the server side of the Techqniques data set decided to imply actually some anonymization before answering the query. So in the other side of this telecommunication, everything seems to be the same. I will query the same thing. But this time I created another function calling a check query on anonymous data. So in this case here, what we are doing, we are actually applying generalization of key anonymity. So I took the age this time and I apply some kind of a binning on it. So we have now 3 groups. I will not return as I used to be returning before direct age. And in this case, just only applying this, see the effect, what would it look like? So if I would have to run the same exact query, which landed 100% likely that the 2 people in my data set are actually with diabetes. If we run this after the query applied anonymization on age only without considering anything else, look at the huge difference. Now let me share with you again just the first 10 entries. As we said, this is the data set. Now after we done the anonymization on the age, you could see now the ages are not there anymore as they used to be. So I have this 15 years bin age group. So from 65 to 80, 40 to 65, and I'm not sure the exact specific age. So what happened here when I did the query as I done in the previous example, the query remained exactly the same of querying of gender 0, zip code 35, and age 50. Watch carefully the result returned from the server. It returned with almost, how many cases here? Like 10 of them. In the previous was only exactly 2 matching. And then if I look at their diabetes cases, they are also mixed. Now in my data set, there are only 2 match 100%. I know these 2 are inside this. I am very sure that 2 of these guys are absolutely here. But look at the dilemma now and the probability, how much decreased to identify which one is which one. I'm really unable to do that. Okay. I mean, even I know all the genders are just matching, the zip code matching, but look at the diabetes. It's almost 50%. So first of all, I don't know which one is which one. And next thing, I have to calculate exactly how much probable that this person actually had a disease based on this given information. It becomes quite a bit complex probability problem end of the day. And it becomes slim chances that I am telling the right answer anyway. So you could see this only with applying K anonymity on the age, how much effect I could get the result only on querying the data set as we have done before. So we have come to the end of this session. I hope now the technique of anonymization and the application of it is quite clear to you. We will be proceeding with the next outline that we set up to accomplish in the next session. That's exactly what we're going to do. Until then, stay well. Cheers.